video, we are going to talk about the differences between fixed point numbers and floating point numbers. And then we are going to find the IEEE 754 standards to represent such floating numbers. So first of all, what are fixed numbers? Well, when you're talking about fixed numbers, that's a dark one. So when you're talking about the fixed numbers, what you have to keep in mind is that the number of decimal numbers, yeah. So for example, are fixed actually. So what I'm trying to say is, let's say we have 356.234. Well, here we can see that there are three digits which belong to the decimal part. Okay, the point is fixed. Okay, it is not recurring. It is not irrational. Okay, this is a fixed number. Okay, the number of digits after the point is fixed. Okay, after this point is fixed. Okay, but in floating numbers it's not the same. Okay, so why do we need floating numbers? Well, floating numbers, okay, so as I said, floating numbers are numbers where the digits after the point, okay, is not fixed. So if you're thinking about pi, okay, we know pi is equals to 3.14159.265 35 and I think 897 141592653589793. Yeah, 89793 and so on. It goes so on. Okay, so this is a floating number. Why? The number of the digits, okay, the number of digits after the decimal point or the point is not fixed. Okay, not only these numbers, very small numbers. For example, let's say we have a number like 0.0000000000001. Okay, if you are representing a very small number, well, you need floating number representation. Okay, or even a big number. So for example, if you have something like 3 8 4 9 3 2 1 7 9 3 4 6.379. Well, this is a large number, right? This is comparatively a large number. So for this, you can use the floating number to represent the given number. Okay, you can use floating number representation to represent this given number. Okay, so this is the difference between fixed numbers and floating numbers. Okay, so how do we use the floating numbers? Well, in floating numbers, we are talking about IEEE, Institute of Electrical and Electronic Engineers. Okay, yeah, IEEE. There is a standard called 754 standard. In this standard, there are two ways of representing floating numbers. One is 32-bit system. Okay, one is 32 bits system and the other one is 64 bits system. Okay, so in 32-bit system, there are three main parts. Also in 64-bit system, there are three main parts. So I will talk about the three main parts. First of all, the sign bit. Okay, we know what a sign bit does. Yeah, sign bit is for representing the sign. Okay, and then we have the exponent. Next, we have the exponent. And finally, we have the mantissa. Okay, so what are the three things? Sign bit, exponent bits, okay, exponent bits. Then we have mantissa bits. Okay, so these are the important things, okay, in a given floating point representation. Okay, in a given floating point representation. First of all, let's talk about the sign bit. Okay, we have not gone through inside it. Okay, we are just focusing on what we are studying here. Okay, so first of all, sign bit. What is a sign bit? Well, a sign bit is the bit that we use to represent the sign of the number. If it's a positive number, we use the bit 0, and if it's a negative number, we use the bit 1. Okay, so this is how you are going to use sign bit. So how many sign bits do we need? Only one bit. Okay, only one bit. So what are the other bits? Well, exponent bits. Okay, I'll just say EXP bits. What are EXP bits? EXP bits represent the power of the number. Okay, the power of the number. So for example, what do I mean by this? Well, let's say you have a number. Okay, let's say you have a number like 39473.23. Okay, you must have studied in your early stages that this can be written down in the scientific form or the standard notation. Okay, it will be equals to 3.947323 into 10 to the power 4. Okay, or you can write it down as 3.947323 E04. Well, you can say positive 04. Okay, or negative. In this case, it is E positive 04. Okay, so this is what we call the standard form. See, this 4 represents the exponent of the base. Okay, so it's the power of the base given here, the index given here. Okay, so exponent bits represent the power of the number, the power of the number. Okay, exponent represent the power of the number. In 32 bits case, okay, in 32 bits case, we allocate 8 bits for exponent, and in 64 bits representation, we represent 11 exponent bits. Okay, we use 11 exponent bits to represent the power. Okay, before you misunderstand, I want to clear this up. I just gave this as an example. Okay, this is just an example. The 32-bit representation or 64-bit representation is for the binary number system. Okay, binary number system. Binary number system. So whose power are we talking about? 2's power. Okay, 2's power is what we are talking about. Okay, 2's power is what we are talking about. So keep that in mind. Don't make a mistake there. Then we have Mantissa. Then we have Mantissa bits. Okay, for 32 bits representation, we have 23 Mantissa bits, and for for 64 bits representation, we have 52 Mantissa bits. Okay, Mantissa bits. So what is even meant by Mantissa bits? Well, Mantissa bits, the things that you have after the decimal point. Okay, this point, after this point, we have several numbers, right? This is what we call Mantissa. Okay, so in binary, it's going to look like 1.01101, something like that. Yeah, it's going to look like something like that. This is what we call the Mantissa bits. Okay, we have 23 bits to represent in 32-bit system and 52 bits to represent in 64-bit system. Okay, so this is the basic idea you should have. In this video, I'm going to mainly focus on 32 bits. I'm not going to focus on 64 bits because if you understand 32 bits, it's more than enough to do 64 bits question also. Okay, so let's start. How can we do this? Okay, so let me draw a rectangle. Okay, let's draw a rectangle. Okay, so now we know the first bit is for sign and the next 8 bits are for exponent. And then we have 23 bits for Mantissa. So this is for sign. This is for exponent. This is for exponent. And then finally we have Mantissa. Okay. So normally why we are using IEEE 754 32-bit standard? Why do we use that? To represent decimal numbers in binary numbers. Okay. Represent decimal numbers in binary system. Okay. So decimal number system to binary number system. So how are we going to do that? Well, let's say we have a number like 10.625, positive 10.625. So how can we write this down in the floating point representation of 32 bits IEEE 754 standards? How can we do that? Well, first of all, we know how to convert this number. First of all, we have to convert the integer. Then we have to convert the decimal part. So first of all, let's convert integer. So we know 10 to the base 10. This is in base 10. 10 to the base 10 is equals to 1010 to the base 2. Okay, and 0.625 can be given as, first of all, we have to multiply it by 2. If I multiply it by 2, what do I get? 1.250. If I multiply it by 2, okay, so here it starts with 0, okay, but if you are multiplied by 2, you get 1 here. So 0.625 to the base 10 will be equals to 0.1, okay. So if I multiply it by again 2 again, it will get the 0.500. Okay, so it will be 0. Then it gets 1.000. So it will be 1. Okay, so this is 0.625 to the base 10 is equals to 0.101 to the base 2. Okay, so what is the number? Positive 10.625 to the base 10 in terms of the equivalent for this number in binary can be given as 1010.101 to the base 2. Okay, now we are going to represent this number. We are going to represent this number in 32 bits standard of IEEE 754 represent floating point representation. How are you going to do that? First of all, we have to write this in the scientific notation. Okay, so how can we write this down? As we normally do in decimals, we are going to do in binary also. Since we have 1010.101, what you have to do is you have to bring the decimal point here. Okay, you have to bring the decimal point such that you have 1 before the decimal point. Okay, it's very important. So you will get 1 point, this will be equals to 1.010101 into 2 to the power 3. Why is it 2 to the power 3? Because we are bringing the decimal point or the binary point in this case, binary point 3 places forward. Okay, we are bringing the decimal point, the binary point 3 places forward. Okay, or you can understand like, since we are, so here we have 1010.101. Since we are moving the number 3 places to the right, okay, since we are moving 3 places to the right, and right is the direction, positive direction, we have 2 to the power 3. Okay, the power is 3. So 1.010101 into 2 to the power 3. Okay, you can use any method. So this is the standard format. Okay, this is the standard format. Well, perfect. Now, what is the sign? Since the sign is positive, we have to put 0 here. Okay. Since the exponent is 3, we have to put 0, 0, 0, 0, 0, 0, 0, 1, 1. Yeah, because it's 3, so we have to put 0, 0, 0, 0, 0, 1, 1. Okay. If you put like that, that's wrong. Okay. Before we write down the exponent, okay, before we write down the exponent, we do a small intermediate step called biasing. Okay, we do a small intermediate step called biasing. What is biasing? Okay, what is biasing? Or we can say XSK method. The method that we use to bias the exponent is called the XSK method. Okay, XSK method. So what do we have to do? Well, in this case, the exponent is equals to 3. Okay, exponent is equals to 3. We have to add a specific number to it. We have to add a specific number to it. What is that specific number? Well, that's what we do what we find out by using the XSK method. What is the XSK method? Since we have 8 bits for exponent, so we have 8 bits. So k is equals to 8. Okay, k is equals to 8. So what you have to find is 2 to the power k minus 1 minus 1. This is the number that we are going to add with 3 in this case. Okay, so 2 to the power k minus 1 minus 1, which is in this case 2 to the power 8 minus 1 minus 1. So it will be 2 to the power 7 minus 1, which is equals to 127. Okay, so if you add 3 to 127, what will you get? 3 plus 127 will be equals to 130. Okay, now you will represent the exponent. Okay, now you will represent the exponent. So that will be 128, no 64, no 32, no 16, no 8, no 4, only 2, no 1. Okay, see 8 bits are covered. Why do we have to bias the exponent? Why do we have to bias the exponent? It's a good question. Why do we have to do that? Well, think of it. Okay, if you just directly put 3 here, okay, for 3, if you directly put 3 here, okay, if you put 3 here, think if you have minus 1, what will you do? If you have minus 1, what will you do? Well, you can't represent minus 1. Since if you put 3 directly like this, okay, that means you can only represent positive numbers. You can't represent negative numbers. That's why we do the biasing method. Okay, so even if you have minus 127, you can add 127 and that will give you 0. Okay, that will give you 0. So that you can represent. Okay, so the power that you can represent is from minus 127, okay, 2 to the power 128. Okay, you can represent until 2 to the power 128. Okay, so that's why we have to bias things. Okay, that's why we have to bias things. You have to keep in mind. Okay, you have to keep in mind. Okay, now we'll talk about Mantissa. Well, in this case, the Mantissa is just 1, 2, 3, 4, 5, 6. Yeah, only 6 bits. You'll write down the 6 bits. Okay, you'll write down the 0, 1, 0, 1, 0, 1. Okay, after this, after these 6 numbers, after this 6 digits, okay, you have to complete the Mantissa. Okay, since there are 23 bits for that, okay, since there are 23 bits allocated for Mantissa, you have to put zeros. Okay, since we have 23 bits for Mantissa, we have to add 17 zeros. So it will be 17 zeros. Okay, 17 zeros after this. Okay, so this is how you have to represent a floating point number. Okay, in the floating point representation, IEEE 754 representation. Okay, so yeah, that's all you have to keep in mind when you are representing this. So let's see another example. Okay, but this time the steps are going to be direct. Okay, straightforward. So first of all, what are we going to do? Let's say we have something like minus 324.125. How can we do this? Okay, first of all, we have to convert this to binary. Okay, so 324 will be equals to 256 and then no 128, and I think we need a 64. So if you add a 64, you will get 320. Then you have only 4. So no 32, no 16, no 8, only 4, no 2, no 1. Okay, so this is equals to 324. Well, 0.125 multiplied by 2 will give you 0.250, multiplied by 2 will give you 0.500, multiplied 2 will give you 1.000. So 0.125 can be given as 0.001, 001 to the base 2. Okay, so minus 324, I'll erase this. Okay, so minus 324.125 to the base 10 will be equals to minus 101,001,000.001 to the base 2. Okay, so what is the next step? Well, next step is writing down this down in the scientific format. So it will be minus 1.01001000001 into, okay, these two into 2 to the power how much? We are moving in right direction. 1, 2, 3, 4, 5, 6, 7, 8. 8 digits. So it will be 2 to the power 8. Okay, so now what we have to do, we can directly write the answer. Oh, first of all, let's bias the exponent. So it will be 8 plus 127. So that is equals to 135. Okay, and the mantissa is already ready and the sign is negative, so it will be 1. So the sign magnitude will be, the floating point representation will be 1. Okay, and for 135, we have 128, no 64, no 32, no 16. But we don't also need 8, we need 4, we need 2, we need 1. And then the mantissa 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. And there are only 11 bits here. There are only 11 bits here. So we have to put zeros until 23 bits, which means 12 zeros. Yeah, 12 zeros. That's it. This is the floating point representation of negative 324.125. Okay, so this is a very important thing that you have to keep in mind when you're doing practice questions. Okay, yeah, keep it in mind, and we'll meet in another video. Thanks for watching the 17th video in our number system series. If you found this tutorial on the IEEE 754 floating point standard helpful, don't forget to like, share and subscribe for more lessons. Hit the bell icon to stay updated with our latest videos. Check out the full playlist to master number systems and follow us on Instagram. I'll see you in the next video. Until then, keep learning and stay curious. Bye-bye.